Welcome everyone to this course. My name is Dr. Manoranjan Oza, Assistant Professor, Department of Basic Science, Chemistry, SR University. Today's topic is optical properties of the solid materials. So we'll discuss here how the materials is interact with the lights. So if you see the different kind of a light region or wavelength of the light, so it ranges from 100 meter to 0.001 nanometer in total wavelength range. From this part, if you see that smallest part, which is the visible regions, normally 350 to 750 nanometer. These are the visible range where you can see the light colors, and other part we can't see in the light. So what we are talking here now will describe that when that electromagnetic radiation, that light is coming and interacting with the materials, then what are the properties we are going to see the changes in the materials. So basically we are seeing the interactions of the electromagnetic radiations in the mainly for we are discussing here ultraviolet or visible light and the infrared light. So these are we are going to discuss here. So what is happening, or what our main point is that we are talking about the interactions of the photons or the light electromagnetic radiations that is coming and interacting with the materials. Then what are the changes is taking places. So inside the material, maybe what they can do, they can change the vibrations of the lattice. Also it can change with the presence of the defects. Also, it may change the electronic structures of the materials. So due to these changes, the properties of the material will be changed. And as the properties of the material is changing, then it can be used for the different purposes. For, let's say, for optical fibers, or for lasers, or for photo detector, and solar cell light emitting diodes, that is called LED, or display technologies, photo crystals. For different purposes it can be used for about understanding these material properties. Right, one by one we'll discuss in these sections. So first question is that when that light is coming and interacting with the solid materials, then what kind of the interactions or the process can takes place. So let's say from outside, this is incoming light. So it is coming and we have here this material. This is our material. And this incoming light is coming here. This is incoming, all our incoming lights are coming. Then what are the process can take place here? So first process can be takes place here is that maybe light is coming and it is totally reflected or bounce back from the material surface. So that process we call is the reflections. So reflections means completely bounce back from the material surface. So that is process is called reflection. In this reflections process, you will see will generally seen in the inside the metals. For metal cases, we see like this, because when it is reflecting completely, the materials we see, it's like a completely shiny. So materials and the metals are looks like very shiny, means the light is coming and it is interacting in the surface, and the light is reflecting or bounce back from the surface of the materials. So these properties is mainly observed in the metals, and we saw in the shiny nature of the materials. Now second one is the transmissions. What is the transmission? So that let's say this light is coming, incoming light, and it is passing through the materials. So means outside from the it is crossing the materials, then we'll see the outside lights is going. So this process is called transmissions. So when the incident light is coming and passing through the materials, that we call the process is called the transmissions. Right. So what is called the absorptions? Absorption process is that let's say inside this incoming light is coming, and that this material has a property. So what it does, that it absorbs the complete light. So it is not going outside of the materials, it stays inside the material, and material absorb the complete the lights. So that process we called is called absorptions. Now, second is called scattering. What is the scattering? Scattering means, let's say it is absorbing, the incoming light is coming in the one material surface, then it is in different directions, it is going out. So this is scattered in a different directions. That process is called the scattering. So incoming light come and interact with the material, and it randomly in different directions the light is scattered. So this process we call it the scattering. And last thing is the refractions. What is that refractions means? Let's say one light is coming. Incoming light is coming here, for example, this is one incoming light is coming, then it is interacting with the material, then after the interactions with the material, then outside the light is going with different speed. This is speed of the material is changing. So if it is coming this speed, okay, then it is like this, it is going. So let's say this one or this one it is going. So it is going out from the outside the materials, but in a different speed. So that we call the refractions. Generally, for let's say we are putting on a straw in a glass. This water is there, and we put the straw here. So what we observe, that the straw when it is going to the inside, it looks like from outside is bent. It is bended. So we call this process is refraction, because the speed of the light came inside, then in water it is bended in different directions. So we see that's like a straw is bended, is becoming bent. So this process we called is the refractions process. Right, so means that light is coming traveling in the different velocity or speed in different medium, and when we observe this property, we call the refractions property. So these are the process can takes place, that reflections, transmissions, absorptions, scattering, and refractions. These are the process can takes place inside in a materials when it interacts with the light or photons when it is coming, and according to it, that properties of the material will change, and the in and it can be used for the different purpose by knowing that what the properties in the materials is changing, and what could be the beneficial that properties for our practical applications. Now here we little bit discuss that, we just discussed, that is called refracting index. So refraction process we are just measuring here. That's unit we call is the refracting index. So how much the refraction process is taking place, that quantity we want to measure, that is called our refractive index. So how it is? Let's say this is our sample. Is and then light is coming from this side, then after that coming this, let's say this is the speed it's showing, then again it is like this, it is decreased little bit, then it is going out again. So the same speed came after the passing to the materials. So previously first it is coming, or you can consider like this. Let's say we are making a straight line here. So this is a straight line it is matching, but if you here, if you see, this is little bit bended. So mean like is coming like this, then it is little bit slow down. This is little bit slow down, then it will go out. So when this process is happening, we call it the refractions of the light, and we are measuring by using the unit n value, and this n is that here c is the speed of the light in vacuum, means no medium is there, only vacuum is there. There we are measuring the what is the speed of the light, that will be the maximum speed. Now inside the material, how much the speed, means here we have taken this is the material, And when it is traveling inside of this material, then what is the speed? When we are dividing these two terms, then we are getting the refractive index. Right, that's how we are we calculate the refractive index. Now, these properties for the basic, for more importantly semiconductor materials, it significantly we see the changes, means significantly bending occurs for the lights. And it also depends on different kind of, means it depends on variant wavelength, means how much it will bend depends on completely how that wavelength of the light which we are going to pass on. And also we'll get to know this what is one phenomena called it dispersion or rainbow like color. We'll discuss in later. We can also see because of these properties. Extinction coefficients. Extinction coefficient is that for which the light is absorbed within a material. So that one we want to measure it. But previously we are discussing that how much it is slow. That is called our refractive index. But what in this slide we are discussing that we want to calculate or wants to know that this material, when light is coming and interacting the materials, then one process we discussed, that is slow, it is absorbed. Let's say this incident light is coming, then it is completely absorbed, it is not going out. Then we also know that how much it is absorbed inside the materials. So that process we are going to calculate using called extinction coefficients, and it is determined the value, the higher the K value of the material, that will be the higher extinction coefficients. So how we are actually calculating, we are using these equations. It is a complex number. Complex number we are saying because if you correlate this one, this is, let's say z equals to x plus iy. So what we introduced one imaginary number here, I and k. So this is that's why it is called a complex number. So here two things is participating in this equation. One is n, that previously we discussed, that n equals to c by v, that is refracting index, plus extinction coefficient. Both together properties we are taking to understand the properties. So one is for the refractive index, another part is called the extinction coefficient. So one part is that how speed is changing, and another part is that how much inside the compound it absorbs the photon or electromagnetic radiations, how it is absorbed. That we are totally calculating by using these equations. So now absorption coefficients, how we can calculate it. Let's say from here light is coming and then it is going out, then intensity, how it is changing. Before, what is the light intensity before the interactions of the materials, and after the materials, what is the intensity of the light. So that's that way we are calculating the absorption coefficient. That equation is used, equals to I equals to I0 e to the power minus alpha x. So alpha here is absorption coefficient. So here I0 is means that I am passing a light from a source, that I know that intensity of that light. Then when we pass through the samples, then the samples absorb some amount of light. So after the absorptions of the light, remaining light will pass through the material. So it is a remaining, that is called I. So this is I. So now what is the three processes taking places? Two processes taking places. One, after the interactions, that some amount of its absorption also is taking places, and then transmission is also taking places. But in transmission, that intensity of the light is much lesser than that of the incident light, right? And how much it is absorbing, that we are calculating by the using the quantity or the constant value, that is called the absorption coefficient of a materials. And we can use that equations, I equals to I0 e to the power minus alpha x, means this equation we can use it. So here I value is known to us, we can measure, and this is the our source light intensity we can measure, and we know then that x value, that is the length of the this is the length, what is the material is travel, this is the length x, this is known for us, then alpha we can calculate. So what we can do, we'll take a log for ln in both sides, then it will be ln I naught e to the power minus alpha x. So then what will happen? Ln I equals to, it will be ln I0 minus alpha x. So we'll plot the y equals to mx, then we'll get the slope. From the slope we can calculate the alpha values from here. So this is our known, or this is known and this is known. We'll put the value, then we'll calculate the alpha value. Like this we can calculate. Now that when a light the photon is absorbed by the materials, then inside the materials what is happening? So in the molecular level, what is the process is taking places when a materials absorb a light or photon? Then what are the processes taking place inside? That one we'll discuss here. So inside the molecules, there will be different kind of a state, that electronic state or vibrational state. So vibrational state will be there, electronic state will be there. So then what will happen, that when incident light is coming inside the material, there will be different kind of a electronic state, let's say E0, S0 or S1 or like this. And inside of the electronic state, there will be vibrational state. So let's say this is ground state, this is a fast excitation state, like this. Now when a photon is coming and interacting with the ground state, what it can do, it can supply that energy to an electron, that electron transition can take place. So this process we call the electronic transitions. So new photons is coming, that is interacting in the ground state the electron, and it is pushing that electron to the higher energy state, that is called electronic transitions. And another thing can happen, that called vibrational transitions, means inside this one electronic state there is many vibrational state. So what can do, it is not changing the vibrational of the state, but what it is changing is the vibration, not changing the electronic state but changing the vibrational state. So let's say in a electronic state, this one small vibration state is there. So and this is one v0, v1, some v2, like this v3. So electron can transfer from only one electron state to v0 to v1, v1 to v2, or v0 to v2, like this transition can take place. This transition we call the vibrational transitions. Excitonic transition is that, let's say one interactions with the materials is happening, that from the outside it is coming photon, then it is interacting with the electron, then electron is going outside. So then a hole will be created, that when a electron and hole pair is created, that process we called is called exciton. So exciton exciton is a combination of hole and electron. So it's a one pair where hole and electron is there. So this we call the exciton. When this kind of interactions or transition is taking places, we call this process is called excitonic transitions. Right, and what can also happen due to the defects in the materials that we discussed earlier, that materials have a different kind of a defects. So due to the different kind of a defects, that interactions of the materials with the photons may change, and we can get a different properties. Right, these are the process or the steps or can happen, or the changes in the molecular level can happen inside of the materials. Right. So because by understanding this kind of a process, what is happening, then we can get to know the applications of the materials, whether it can be used for protective coating or plasma device or mirror or something like that, etc. More importantly, we'll discuss here one sections of the material is called semiconductor. So previously we observed that this when metal is there, for that metal, that conduction band and valence band, they are mixed together. So electronic transitions can happen very easily for them. So this is, let's say, valence band, and this is your conduction band. Is so for metal it's very easy to transfer the electrons from conduction band, valence band to the conduction. It's very energy gap is very close and they are mixed together. But in semiconductor there is little bit difference is there, but if you are providing sufficient energy into the conduction band, valence band, then electronic transition can happen from valence band to conduction band. But for insulator, this energy gap is very high, so it cannot give the much more energy, or it can't with this electron from the ground state to the valence band to conduction band, electronic transition can't be done. So this compound we call is the insulator. So now here we are discussing this kind of a material. There it has some difference energy gap between the valence band and the conduction band, but this that can be overcome by the using energy from the photons or something, photons from the outside, to excite the electrons from the valence band to conduction band. So there are two types of the excitations can happen in the semiconductor. One is called direct and another called indirect. Direct conduction when happen, transitions happen, electronic transitions happen from that there is without changing the momentum, means this is the maximum level of the uh, valence band and this is the minimum level of the conduction band. So directly when transitions happen from the maximum positions of the valence band to the conduction band, then this kind of the transitions we call the direct transitions or direct band gap transitions. But here if you see in this material, when there is no such kind of a direct transition is not possible, so it's a helping with the vibrational, then transitions happen. This process we call the indirect band gap semiconductors. Right, this is generally happened with the silicon or germanium, whereas the direct band gap happen with the gallium, arsenium, for this kind of a compound, and it is used for the LED purpose or laser diodes. When the direct like this, so from when the momentum is without change in the momentum it takes place, that is called direct band. But here is the momentum is change takes place and the vibrations is takes also part for these transitions. And in insulator there is no such kind of a transitions happen because the energy gap is very large. So generally more than 3 electron volt is the energy gap. Right. So this property and this is property is useful for the optical windows or lamps or insulating materials. So now here we'll discuss that electronic transition in solid. So in this electronic transitions occur, that what just now we discussed, that there is two band where the electron is full, we call it the valence band, and then when electron will go that empty space, empty band where that electron is not there but can be accommodated, that this process we call the electronic transition. So transition is taking places from the valence band to conduction band. And just previously we discussed so that when a hole and electron pair is formed, so this process is called, this one state that is called excitons. So this is called the excitons. So what kind of the transitions here we are looking for? It's called interband transitions, intraband transitions, and the excitons. So in interband transitions meaning that is Valence band to conduction band, that only the transition is happening, that is called is the interband transitions. But in the same energy level, if the transitions taking place in the same energy level, and that process we call is called the intraband. Here if you see intraband, that this is one transition state and this is another transition state, that is called interband. Means it is transition is taking place one band to another band, but in sim only within that band, one band, if small from as an interaction is taking places, that we call intraband transitions. And if one kind of a pair with electron and hole is prepared, is formed, so this kind of a bound state which is called the excitons. So there holes and electron pair formed. Now it's called dispersions and optical spectra. What is the dispersion is, let's say one light, white light, it is coming through a prism. This is a one prism, and then outside of the prism we are getting rainbow or waves here different. So white light is the mixture of seven colors, seven wavelength of light, so it's a white light. Now when it is passing through the other part of the prism, that light is separated based on their wavelength, so we are getting a rainbow type different colors. So when this process is happened, we call the dispersions. So this is happening due to the different lambda value, right? Wavelength different, so speed of the light will be different and is separated when it is passing through the prism. So this process is called dispersions process. So when d lambda, this value d lambda by dn value is less than 0, so then what is happening, if you see here, what we are going to say, that how much it is bending. Let's say this white light is coming, then after the passing the prism, so if you see that blue light which is having smaller lambda value or wavelength is smaller, that is bending much more, and whether the red light where is lambda wavelength is high, that is bending less. So this process, when the bending of the light is directly proportional to the inversely proportional to the wavelength, means higher the wavelength, lesser the bending, lower the wavelength, more the bending. This process we call is the normal dispersion, means bending is happening, dispersion is happening, but that depending on the wavelength, that wavelength is higher, then that light will disperse or will bend very less. When wavelength is higher, is lower, then the bending will happen more. So this process, when it takes place, we call this the normal dispersion. Anomalous dispersion is that it is not following the equations, or what we will say, we'll repeat here, that lambda in this wavelength of the light, it's, if it is wavelength of the light is higher, then dispersion should happen less or bending should happen less, and if wavelength is lesser, then bending or dispersion should have high. But in anomalous, it is happen in opposite way. So in anomalous dispersion, what happen is that smaller wavelength light bend less, and less wavelength of light bend less wavelength of light bend less, and more wavelength of light bend more. This opposite of the normal dispersion takes place. So this process we call the anomalous dispersion. So anomalous dispersion happen because of that when the transitions or polarizations takes place at the band gap and occurs the absorption band. So because of this electronic transitions, this kind of the anomalous properties is observed. So, and the dielectric function in the sample we measured by using this equation. This is the this epsilon 1 and plus I epsilon 2. That is this the we are calculating here, the one governs the this where the epsilon 1 is governs the polarization and refractions, where epsilon to represent the energy absorptions within the material. So two properties we are taking. One is polarization and reflection, that is epsilon 1, and in epsilon 2 we are calculating the energy absorption within the material. That process we are calculating the dielectric functions of the materials. Now non-linear optical properties of the material. The non-linear optical properties of the material is that, let's say I have a one light source, that light is coming and interacting with the materials. Now materials properties, we are getting something. Let's say its color is changing, or it is glowing or something, or electronic transition is happening in a perfect way. But I am now changing the energy of the light, incident light, or I am changing little bit higher in energy. Then if in the increasing the energy of the incident light, if the material's property is proportionally in increases, then we call it the linear optic properties. Means I am increasing the source light here, which is interacting with the material, and when I am changing the incident light energy, the material's property is changing inversely. Sorry, in proportionally it is changing. That process is called the linear optical properties. So means I am increasing the energy of the light, my electronic transitions is taking place higher. Again, if I am increasing more, again it is transition is taking place higher. If I am decreasing the energy of the incident light, then my material's behavior is also decreasing. So it is linearly behaving. So proportionally it is behaving. That is called linear optical properties. But if happen that in some stage I am increasing a huge energy of the incident light, then this material properties behavior won't increase or won't react in proportional way. Abruptly or sudden change will be takes place in the materials. When these kind of things happen, we call it non-linear optical properties. Means there is no linearly behavior, because I went to a certain conditions where the materials that this properties is not no longer behaving in the linear way. So this process is called non-linear optical properties. So some kind, for example, let's say we are providing some kind of a energy photon, then that photons will interact with the electron, then electron should transition should takes place in this. Let's say this is 1 electron volt, this transition should takes place. But when I use the higher energy little bit more, then it is crossing that limit, then this transitions, when I am making double, that electron transition should happen in the 2 electron volt. But what is going to happen here, more than 2 or 3.5 electron volt or 3 electron volt. So these not linearly behavior, but abnormally or non-linear behavior is observed in the materials after certain limit. This properties is called non-linear optical properties. This effect is essential for application in lasers, optical modulators, and optical switching technology. These are being used. So what is the applications of these materials? The light, what are the materials which is interact with the lights that have it is used in the solar cell. Solar cell, that it absorbs the photons or light, and then electronic transitions happens, and their holes and electron is separated, and then we get to we get the electricity from this one solar cell. And for LED, also optical fiber or LCD or OLED compound photodetector, smart and functional optical coating. For this purpose, this has been used. So here we have discussed the properties of the materials, that is called optical properties. Means we are discussing that one, if light is coming or electromagnetic radiation is coming and it is interacting in the material, then how it is interacting, what is the process it is interacting that takes place, that is absorption, reflection, refractions, dispersions. And This after this process, when it is interacting in the molecule or compound, this molecular level, what are the changes is taking places? Those we have discussed in this section, and what is the applications of those of the molecules or compounds? That's we have discussed. Thank you.